Welcome everyone. It's good to see you all here. And today we are making a recording of a lecture on fundamentals of linear algebra. So maybe when you hear the words linear algebra, what do you first think of? Is it matrices and columns of numbers? So if this is the case, then I'm going to show you that it's not how you should think about it, and that vectors and linear maps are much more powerful and comprehensive concepts than just tables of numbers. And I'll also show you today how we arrive to those matrices and to vector columns. But in order to come there, we'll have to first rigorously define what we mean by vector space and a vector, because I think that not everyone can immediately tell what a vector is. And indeed, it's not obvious. So the first chapter today is vector spaces. Maybe a little motivation to the definition. In real life, whenever we talk about proportionality and we say that some quantity is proportional to some other quantity, what we actually mean, we mean that if you have twice the amount of the first quantity, the second amount also doubles. If you have the sum of two quantities, then the quantity which is proportional to that one would also be the sum of the proportional part to the first summed and to the second summed. So already in this notion of daily life proportionality, we actually use two operations. One is addition, and one is multiplication by a scalar or by a number, like doubling the amount. So the definition of a vector space goes as follows. Definition. A vector space is a triple of a V, a plus in a circle, and a dot in a circle. Now what this is? Consisting of a set V and two operations. So V is a set. It's a collection of anything. And two operations are defined as follows. The first one, plus. It takes two elements of V and maps them again to an element of V. So what is denoted here with the cross is called the Cartesian product, or just the cross product, and it's just a set of all ordered pairs of elements of V and V. So in here, such pairs like VW live, where V is in V and W is in V. And the notation like this is the name of the map, sort plus. It takes elements of a set, V cross V, and to each element of this set, it gives an element, it gives a unique element of the set. And precisely how it works, it takes a pair from here and maps it to an element that we call V plus W. And you know that this is only a notation because this is just a map, and why we write it just in between of two elements, because what we mean by that notation actually is the map O plus applied to this pair of two numbers. But this is only to be very precise by what we mean. And once we know what we mean, we can always write v plus w. So this map is called addition. And well, we haven't talked about any numbers so far. And what I'm going to give you now, so the second map, is actually, we already specify not to all vector spaces, but to real vector spaces. So just in the scope of this lecture, we'll only deal with real vector spaces. And real, in this context, mean that we take real numbers and that our coefficients with which we scale vectors are real numbers, the usual numbers. So the multiplication map takes an element of real numbers and a vector and maps it to a vector. So how it does it? For example, it takes a real number lambda, it takes a vector v, and it maps to lambda dot circ v. So this notation is a standard notation for maps, and this is how it acts on the sets. So from which set to which set it acts, and this is what it does to the elements with a little bar on the arrow. So this is called scalar multiplication. But this is not it. I could take any set and any such operations I can possibly come up with in my imagination, and it will not necessarily be a vector space. Those operations must also satisfy what's called axioms of vector space. And we have 8. And so such that, or maybe even right there, which satisfy the following 8 axioms. I'll now write them down on the new blackboard. So it's said that when we use real numbers as scalars in the definition of a vector space, this is called a real vector space. But in general, we can, for example, use complex numbers, or even more generally, we can use any field. And in this case, it would be called a vector space over a field of, say, real numbers, or over a field of complex numbers. So which satisfy 8 axioms, and there is very convenient abbreviation how we can memorize all of those 8 axioms, and we'll call those Kenny Adu. So Kenny Adu. And now let me show how to open this up. So the first axioms, C. C stands for commutative. So this is the C of our circ class, and it says the following. For any 2 elements, U and V, U circ plus V is the same element as V circ plus U. This is commutativity of the addition. Then next is A, also of the addition. And A is associativity. So if you have now 3 elements, U circ plus the element V circ plus W, then it must be the same as U circ plus V circ plus W. And actually, this is the axiom which allows us to write this expression v plus u plus v plus w without any parentheses, because unless we know that this expression is the same as this one, we cannot write anything like v plus u plus v plus w. This wouldn't make any sense, because the operation of addition we defined is a binary operation. It takes only 2 elements, not 3, not more. But the property, the axiom of associativity, allows us just to write sums and not care about the order how we put the parentheses. The next one is n, and n stands for neutral element. So again, neutral element of the addition. It says that there exists an element O in the vector space V such that for any V in V, O through plus V equals, again, V. So this element, this neutral element of a vector space, is commonly called a zero of a vector space. And obviously, as we expect, when we add 0 to any element, we again get the same element. Now you can immediately see with the first axiom that V plus 0 would also be V, because we have commutativity of the addition. And about the notation, this symbol here, it stands for belongs. So this V is a set, and this O is an element. Here I also used it. And this just means, let me write it in different color, belongs to, or an element of, or maybe element of. And the same here. This symbol here means that there exists, and this is actually just a flipped letter V. Oh, sorry, flipped letter E. And this symbol here stands for all, or for any, and this is just the flipped letter A. So the entire expression reads as follows, that there exists an element O in V such that for any element V in V, O plus V equals V. Just as simple as that. So now let's continue with the axioms. We have can, now we have E. And E means the inverse. So again, this is the E of the addition. And it means that, again, for any element V in V, there exists an element, what we call minus V. And you know, this is just a notation. This is just the name of this element, such that V, O plus, minus V equals 0. So this is the inverse element, and as we expect, this is just the minus of our original element. But we don't have an operation minus. This is just a part of the axioms of a vector space, that for any element, there exists an element such that their sum is 0. Then it comes the A axiom. And this is just the associativity of the multiplication. So if you have two scalars, lambda and mu, and we multiply them in real numbers, we take circ dot, any element v, then it must be the same as first multiplying lambda on the result of multiplication of mu on v. So you see, when we multiply a scalar on a vector, we get, again, a vector. And this is, again, a multiplication of a scalar on a vector, and that's why we denote it with a circ dot. Whereas here, it's just a multiplication of two real numbers. So this dot, it belongs to the dot on the real vector space. Sorry, on the dot on the field of real numbers, not a vector space. So this is the associativity of dot and circ dot. Now come two distributive flows. So the first one is that for any scalar lambda, when we multiply it on the sum of two vectors, this would be the sum of two vectors multiplied by lambda. So this is the distributivity of circ dot and this. Now, the second distributive axiom deals with distributivity over the addition of real numbers. So if you now take lambda plus some other scalar mu, and we multiply the result on any vector v, it would again be a plus, but now in the vector space of lambda multiplied by v, plus of a vector space, mu multiplied by v. So this is the distributivity of the real numbers plus and scalar multiplication. So again, I emphasize that this plus is a plus of real numbers, just the addition of two numbers. And this is exactly the reason why so far we write circ plus and circ dot instead of just plus and dot, because it is very important to keep in mind that those are different operations on a different set that define a different structure. Without circles, it's just the usual operation on real numbers, and here we add elements of a vector space. Those are, for now, abstract elements of any vector space, and those are not real numbers. And finally, the last axiom is U. This is the unity of the scalar multiplication again. So if you take 1, just the real number 1, and we multiply it by any vector v, we again get v. So multiplication by 1 acts as the identity on v. And of course, all of those 8 axioms must hold for all vectors u, v, and w in v, and for all scalars lambda and mu in real numbers. So let's now do a couple of examples, but before that, I finally tell you what a vector is, and the only correct definition of a vector is just an element of a vector space. Not a column of numbers, not an arrow on a plane, but an element of a vector space. So I'll maybe even write it down. So definition: a vector is an element of a vector space. So are there any questions so far about the definition of a vector space, a triple, a set with two operations which satisfy these 8 axioms? Okay. Yes.
Could the vector space be empty or maybe contains only one element? Is it something real?
Well, the only instrument to answer this question is actually checking the axioms. So if you come up with a vector space, and they can, so let's take just an element O, and that will comprise our set V. Let's define the operation of addition, and we can specify how it acts on all elements of V. We have only one, so O plus O equals O. And we have to specify how the scalar multiplication works. And I tell you that any number multiplied by O is again O. And now what is left is to check the 8 axioms. And as far as I see, this does constitute a vector space. So a vector space of just a single element with the operations defined like that indeed constitutes a vector space, although not very interesting. But that's a very good question. So let's proceed with the example. So example, and here's a very important and I would say canonical example. This is the set Rn. So first of all, what is Rn? This is just the set of tuples of n numbers. That's it. So Rn is defined as elements, let me call them x1 to xn, where all of them are just real numbers. So once we have just the set of real numbers R, we can define the set Rn, and you can, I think, already see that it is actually just the cross product or the Cartesian product of R n times. So the set of ordered tuples. So this is Rn. And we don't talk about any addition or multiplication here so far, because we know how to add two real numbers, not how to add tuples of n real numbers. But an element of Rn is just any tuple of n numbers. That's it. For example, 3, 6, square root of 2 is an element of R3. So, but we now can take this as a bare set without any operations yet, equip it with two operations of addition and scalar multiplication, and get the vector space. So let's do it. And there is actually an obvious way how to equip this bare set with operations of a vector space. And so let me define them like that. If I take any arbitrary element x1 to xn, I take another element y1 to yn, and I define the separation as the following element: x1 plus y1 to xn plus yn. So again, a little comment on the notation here. This equal sign with a colon means defined. And note that this symbol has a direction. So we have a colon on the left, and it means that the expression on the left is defined in terms of the expression on the right. And if we wrote equals colon, that would be a different symbol. And it would mean that the right-hand side is defined in terms of the left-hand side. And this is why this symbol is actually better than some other symbols you might have encountered as triple equal sign, or for example, equal sign with a little triangle, because those do not specify the direction. So this one is better, and this one is the one we'll use. So this is how we define the addition of real numbers, and this is called the component-wise addition. Sorry, not of real numbers, but of the vector space Rn. So far, not yet a vector space, but we're making it one. So now we need to specify how we multiply by a scalar. So if you take, again, some scalar lambda, some real number, we multiply it with an arbitrary element over n. We define it to be lambda multiplied by x1, lambda multiplied by xn. So again, here and here, the operations we used are the addition and multiplication of real numbers, because this one is 1 and this one is a real number. And here is a tuple, and here we come up with our rule how to do it. We could obviously come up with some other rule and check whether it satisfies our axioms, and if it does, we are good to go. This is a nice vector space. But this one is quite an obvious way to do it, and it is convenient, and that's why it's called the standard vector space structure on Rn, or the canonical vector space structure on Rn. But it's not given that you can add two elements of Rn, or you can multiply it by a scalar, unless you explicitly define it like that. And importantly, check the 8 axioms that the operation is defined like that, indeed satisfy them. And this is a good exercise. I can tell you the result that it will work, and it's good to check it yourself. So another example of a vector space is, for example, the set of smooth functions. For instance, so let me denote it as C infinity Rn R. Those are functions that take elements of Rn, just as a set, and return elements of R, just as a set, such that they are infinitely many times continuously differentiable. So, for example, a function from Rn to R would be an element of this set if it's smooth. Good. So now let's equip this set with the operations. And it's again not very difficult to do. And we'll do it pointwise. So for any point x in Rn, we define it that f surplus g, so this would be a new function. We expect it to be the new function, and we need to specify how it works. And we specify it at any point x, it must be equal to, expectedly, f of x plus g of x. So again, we define our addition on this new set in terms of the addition of real numbers. And the same thing comes with the scalar multiplication. So lambda circ plus, circ dot f at the point x must be equal to lambda dot f of x. And again, one can check, and you should, that operations on this set defined like this indeed satisfy the 8 axioms of a vector space. So this is just a few examples, and again, this structure is called a standard structure on the space of smooth functions, and in the space of just any functions between Rn and R, we could also define the similar pointwise operations of addition and scalar multiplication. And they are often considered given, although one has to first define them like that, make sure that this is indeed a vector space, and only then talk about any addition or multiplication. So, and also I said that a vector is an element of a vector space. So in this case, a vector is indeed a set of n numbers. And that's why many people have a perception that vectors are, for example, columns of n numbers. And here, a vector is a function. So a function can as well be a vector. There's no problem in that at all. So now we introduced a structure. It is a mathematical structure of a vector space. And it's quite often to define it in terms of some sets and some operations which satisfy some axioms, as we did here. And usually, once we define some new mathematical structure, we study maps between such structures, and specifically maps that preserve the structure, so-called structure-preserving maps. And in the case of the vector space, which is also sometimes called linear space, those maps will be called linear maps between vector spaces. Thus, the maps that preserve the structure of a vector space. So this is, once I erase the board, we'll do that. So as I said, after we defined a mathematical structure, we studied the structure preserving maps. So if you're given two vector spaces and a map between those two sets, how does it play with the structure of a vector space? And that would be the definition. A map between a vector space V, and I'll denote vector space just with the letters Vs, or vector space V circ plus circ dot and a vector space now W, and here we have box plus and box dot, and this another set, another operation, other operations, and just simply a different vector space. So I use different notation to really stress this out. A map is called a linear map if it satisfies the following two conditions. So as I said, linear maps in this case is a structure preserving map. So we expect that it takes structure from here and somehow translates it to the structure to here in a way that respects the structure of a vector space. And in case of a vector space, this is the addition and scalar multiplication. So if our map let's call the map phi and it will be actually from the set V to the set W. So a map phi from V to W, where V and W are two vector spaces, is called a linear map if it satisfies first that phi applied to the addition of two elements, so V squared plus W, is equal to phi of V, and now comes the addition of the new vector space of W. So this is the box plus phi of W, and that phi applied to some real number lambda multiplied with V must be equal to lambda, now box dot, phi of V. So those operations are on the vector space W and those on the vector space V. And this, of course, must hold for any V and W in V and for any lambda in real numbers. So this is the definition of a linear map. We could also show some properties. For instance, if a linear map is invertible, so if phi is a bijection, so proposition, if phi is bijective, then its inverse is also a linear map. Actually, in this case, when phi is a linear map and it is bijective, you see that the inverse is also a linear map. In this case, phi is called a linear isomorphism. Oh. So a bijective linear map is called a linear isomorphism. And now one more property, and even this is again a proposition which one can prove, that a composition of two linear maps is again a linear map. And compositions, they are denoted with a little circle like this. And I'll now explain what it means. So a composition of two linear maps is a linear map. So now on the notation. If I have a map phi which acts from, for example, U to V, and we have another map psi which acts from V to W, then we can always construct a map which first takes phi, then applies psi to the result of phi, and it is called psi after phi. So this little circle, it is very convenient to read it as after. And this would be a map, in this case, from U to W. So in symbols, we can write it that psi after phi on some element u is just psi applied to phi of u. So this is the composition. And if both of the maps phi and psi are linear, so we have three vector spaces, then their composition is also a linear map. And it's very useful. So if you have now many different vector spaces, then you can go with one to another using the linear map, and it preserves the structure of a linear map. It preserves the structure of the vector space. You can compose such map and the structure would still be preserved. And if the map is invertible, then the inverse also preserves the structure. So now let's give a quick example of a linear map. And this one again is a map you're all well familiar with, namely the differentiation of functions. So for example, let one set be the set of all continuously differentiable functions, say from R to R. Another set is just the set of all continuous functions. So this one above C here, it just means that one's continuously differentiable, and here is 0, just denotes continuous functions from R to R. Then D, the map D, which actually, okay, let me write it here. Then D, which acts from differentiable functions to continuous, and it takes a function f and returns a function d f or dx, is a linear map. So again, what should we do to prove that claim is to check the definition. So does it satisfy, does it preserve the structure? Does it preserve the addition and multiplication of those two sets? And you see that I already implicitly used some structure on those two sets. There I used exactly the pointwise addition and scalar multiplication, which I defined for smooth functions before. So whenever we write it and use them as vector spaces, we imply that we use this standard structure. So if you take the sum of two functions and derive them, the derivative, then the result would be equal to the sum of the derivatives of the two functions separately. And the same works with the multiplication on the scalar. If I multiply my f by some scalar lambda, then it just would be the lambda times the derivative of f. So this is indeed a linear map, and just one example of it. So far, we only talked about abstract vector spaces and linear maps between those abstract spaces, but we are mere humans, and for us, it is often much more convenient to work with some numbers. And that's exactly where those matrices and columns of linear algebra come into place. This is the talk about components. And to talk about components, we must first define what is a basis of a vector space. So we proceed with the second chapter, basis in vector components. And I write basis in plural form. So definition. A basis. And this is really going to be not maybe the most obvious definition, but try to follow, and it will be indeed you'll get the point. A basis of a vector space V, and now let me drop the circles in the notation, because now we are mature enough to really distinguish the operations of a vector space and of real numbers. So here let me use just the ordinary plus and dot. A basis of such a vector space is any subset B inside V. So this symbol means a subset. Let me such that the following two properties are satisfied. So the first one is called finite linear independence. And it's stated as follows. For any finite subset E1 to EK. So here finite subset really means that the set of some natural number of elements or zero elements. That's why I can write it like that and enumerate them from 1 to k. So just a set of k elements in the basis B. So for any such finite subset, it is linearly independent, which means that if there are some lambdas such that E times lambda 1 times E1 plus lambda 2 times E2 and so on plus lambda k times EK, if that turns out to be 0, then it must necessarily mean that all of my lambda 1 equals lambda 2 and so on equals lambda k equals 0. So we had some subset B. It not necessarily has to be finite or even countable, but for any finite subset of B, the following property must hold, that if there are such numbers lambda, which the linear combination with those lambdas of E1 to EK equals 0, then all of those lambdas must vanish. So this thing is called linear combination. This sum. So this is the first property. And the second one, after all, this is a basis, so it not only must be a linearly independent or finitely linearly independent subset, but it also must generate the whole vector space. So the second one is generating property, which means that for any vector v in my vector space V, there exist, and now I also say that there exist finitely many numbers and a finite subset of B. So there exists subset E1 to, now let me use En in B. So that might be the entire B, maybe only the subset. And n real numbers and now I will call those real numbers a V with a superscript E1 to Vn. So just V is a vector, is an element of a vector space, and with the subscript E1 or to En is just a real number. So for any element V, there exists a subset and there exist real numbers such that the sum from I equals to 1 to n of Vi times Ei, which is just a notation, shorthand for V1 times E1 plus so on Vn times En equals to the element V itself. So you see that our vectors, our elements of the basis here, E1 to En, those are vectors, and this is a linear combination. So basically what we say here, that for any element V, there exists a finite linear combination of the elements of the basis, which generates our vector in question. So this definition might seem strange, because why don't we say that this is just some n elements, or maybe we talk about something about the dimension of the vector space. But the crucial moment here is that we can only talk about the dimension of the vector space after we have defined a basis. But first of all, let me make a little comment. Here, I used this notation and didn't say anything about it. I use the upper indices for numbers or for coefficients, and I use lower indices to enumerate the elements of a vector space. And this is just a very convenient convention and nothing more. But it is a very good practice to keep your number elements up, and you keep your vector, to keep your number indices up, and you keep your vector indices down. So when you enumerate some vectors, as here in the basis, there's a denoted with the down index, and there's a denoted with the upper index. Actually, that will help later on to drop this summation sign and write it like that, the Ei, and we'll know that if you have one upper index and the same lower index, then we sum over this index. But for now, let's keep the summation signs. Also, a little remark. You see, this basis is actually known as Hamel basis, because there's also another definition, which is called Schauder basis, and we're also not going to cover it in this lecture. But what's the difference is that here, in the generating property, we also require that there is a finite linear combination. So here we have n. For instance, you have a feeling that, for example, in the space of, for example, continuous functions on the on the interval from 0 to 2 pi, you have a basis which consists of one of sines and of cosines of different frequency. And you might think, oh, but this is if I have some arbitrary function that I need, in general, infinitely many basis elements to generate it. You need a series. So in this case, in this example of a set with so-called Fourier basis, you actually need in general, infinitely many elements to generate an arbitrary element, an arbitrary function. So here you would write infinity and it would be a series. But that implicitly means that we must need a notion of convergence of a series. Because this sum is defined, it's just the consecutive sum of n elements on our vector space. But if you want to sum infinitely many elements, we must need a notion of convergence, and for that, we actually need a notion of topology. So unless we have a topology, which is an additional structure on the set V on the vector space, we cannot talk about any other definition of a basis or of infinite series here. So on a bare vector space, without any topology, this is the only definition of a basis possible with finite linear combinations. So a Fourier basis on those continuous functions would not be a Hamel basis in this definition. A Hamel basis in this case would consist of many more functions so that we can generate any function with only finitely many elements of the basis. And as I said, the dimension is defined in terms of the basis. So another definition, a dimension of a vector space is just the number of elements of its basis, or the cardinality, so-called, of its basis. So, and we write that d v equals b. So for instance, this could be equal to some natural number n, or it can be equal to infinity. In this case, we say that the vector space is n-dimensional. And in this case, we say that it is infinitely dimensional. Now, the immediate question one should pose here is, but is it possible that different bases of the same vector space have different number of elements? And there is a theorem that one may prove that all the bases of the same vector space have the same number of elements. And that's why this definition is actually well defined. This notion of dimension is well defined. This can be checked and proved. So this distinction that I talked about Hamel basis and Chowder basis and finite generation, infinite generation, it only plays a role in infinite dimensional vector spaces. So if we restrict ourselves to only finite dimensional vector spaces, for example, the vector space with functions we defined before would not fit into here. If we restrict ourselves to only n-dimensional vector spaces, then we just have we'll always have n elements in our basis, and there is no issues with convergence here. So from now on, we restrict, and also for the purpose of this course, we restrict to n-dimensional vector spaces. Which are also called finitely dimensional vector spaces. So only once we have defined a basis of a vector space, we are allowed to talk about components, and this is where those columns of numbers many of you are familiar with come into place. So we start with the definition. And here remember that we restricted ourselves only to finite dimensional vector spaces from now on. So in an n-dimensional vector space, components or coordinates of a vector inside this vector space of vector v are n numbers, but that's not it. So components, and as I said, with respect to a certain basis. And now I'll also introduce a little distinction. So far, a basis is just a set of some elements, and in finite in n-dimensional vector space, it is the set of n elements. But I also want to restrict to ordered basis. So it's not only a set, but it also has a certain order. So there's a first element, the second element, and there is the nth element, and they are fixed. So in an n-dimensional vector space, components of a vector v, and now it comes with respect to an ordered basis and E1 to En. So before, when I wrote just a set of some n elements, I used curly brackets, and here I use parentheses to denote to distinguish that this is an ordered set. So with respect to an ordered basis E1 to En, and this is actually just the part of the defined notion, components with respect to a basis are n numbers or n scalars v1 to vn such that the linear combination from the definition of the basis, from I, the sum of I equal to 1 to n of vi times ei, which is, I'll write this once again explicitly, v1 times e1 plus dot 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 vn times en equals to v. And again, it's possible to check that this notion is well defined, that once we have fixed a basis, that those numbers not only exist, but that they are unique. So this is well defined. And in an n-dimensional vector space, once we've fixed some basis, to every element we can assign the set of n numbers v1 to vn, which we'll call the components of v with respect to the spaces. An example. Consider the set R2 with standard addition and standard multiplication, component-wise addition and multiplication, which we defined before. And I give you an element v equals 3, 5. This is an element of our set R2. Question: what are the components of this element? What are the components of element V? Please.
With respect to which basis?
Precisely. So whenever you are asked what are the components of some element, the immediate question must be with respect to which basis, because you might be tempted to say that they are 3, 5, but that wouldn't make any sense. This is just an abstract element. So now I give you a basis. For example, E1 equals 3, 1, and E2 given by 0, 2. First of all, is this really a basis? Are those two elements linearly independent? Well, yes, they are not a scalar multiple of each other. So this is a linear and linearly independent linear combination. And we have two of them, so we know that they do generate the entire two-dimensional vector space R2. So now let's compute the components of V with respect to this basis. So V, which is 3, 5, is 1 times 3, 1 plus 2 times 2, 0. And you can try, but those would be the unique numbers which you can decompose V with respect to this basis. So this is E1 plus 2 E2. So the components of V is V1 equals 1 and V2 equals to 2. And we will now write something magical. We can write that components of V with respect to this basis are 1, 2. And this is where the column comes. So the components of V with respect to this basis, with respect to the basis E, can be written really as n numbers, but these are 1, 2 is the components of an element 3, 5 with respect to this basis. So whenever you write those columns as such, where those denote the components of a vector, first of all, this must be with respect to some certain basis. Now let's give a definition of a coordinatization map. So it would take the elements of a vector space, and given a certain basis, it will return their components. So definition. The coordinatization map with respect to an ordered basis and let me write EI. And again, we are working in an n-dimensional vector space. Is a map. So I said that it takes, how to note this, psi with a subscript E, denoting that it is a coordinatization map with respect to the basis E. So it acts from the vector space V, takes vectors, and returns its components. Then there's n numbers, then what space this is? The target space of the coordinatization map. Precisely. So it takes vectors and it maps them to Rn. Moreover, proposition. It can be shown that the coordinatization map is a linear isomorphism between the V as our vector space with its own vector structure and Rn with the standard or canonical structure. So proposition, a coordinatization map, is a linear isomorphism. Between what? Between the vector space V with its own addition and multiplication, and between Rn with the standard addition and standard, multiplication. So with the standard vector space structure. And this is a crucial proposition, which turns out to be very convenient in real life. Because what it basically tells us is that instead of working with abstract elements of a vector space, and instead of working in an abstract vector space V, we can always choose a basis, translate all the vectors into Rn, and in such a way that all of our additions will be preserved, all of our scalar multiplications will be preserved, and it will be invertible. So this is an isomorphism, which means that the inverse of the coordinatization map is also a linear map, so we can also go back. So we can do all the vector space business in Rn with the standard vector space structure, and then come back and get our results in the original vector space. And this is exactly why in linear algebra we deal so much with those columns and matrices and components. This is precisely because of this proposition, that we can go to the components, go to Rn, do everything there, and come back and do it in a linear fashion. Although it is always possible to choose a basis and to go to coordinates, one must not be tempted to always do so, and one must not be tempted to always work in Rn, because after all, what the results you get in Rn, they do depend on the choice you made, on the choice of the basis. And this should really be kept in mind when working in Rn, that we have made an explicit choice. And some people say an important phrase: a gentleman only chooses a basis if he must. A gentleman only chooses a basis if he must, which means that unless it is really necessary, for example, you want to write a computer program doing something with numbers and you need to go to Rn, you should not really make this choice, and you should rather work with the original problem and not translate it to Rn. And now, this is the end of the second chapter. And we finally come to our third chapter, which is components of linear maps. So we have defined the basis in a vector space, and we have defined how to coordinatize this vector space and go from vectors to coordinates over n. But we also studied linear maps, so maps that preserve the structure between two different vector spaces. And is it possible to also work with them in components? And yes, it is. And this is precisely where the matrices come up. So suppose we have a linear map. So suppose phi, which goes from an n-dimensional vector space V to an m-dimensional vector space W, is a linear map. And of course, when I say that it's a linear map, I imply that those two spaces must be vector spaces, and this means that I must have specified some vector space structure of addition and multiplication here and addition and multiplication here. But for now, it's not important what exactly they look like, but we know that they are there. So suppose phi is a linear map. Then consider the picture. We have the vector space V, n-dimensional. We have the map phi, which maps us to W. Suppose that phi is a linear map, that E1 to En is a basis of V. And F1 to Fm is the basis of W. Now, from V, we can go with the coordinatization map to components to arrive into Rn. This will be with the map psi E, which we just defined. From W, we can also use the map psi F, which will take us to Rm. And those are two linear isomorphisms, so we can go back and forth and not lose anything. What I will call the component representation of a linear map would be some map phi here, and this is the big phi, and this would be a map from Rn to Rm, which makes the diagram commute. So what does words mean? I draw an arrow here, but what the commutation of the diagram means is that it doesn't matter in which direction I go along the arrows, I get the same result. So in this case, if I first apply phi, then go to components, this must be the same result as if I first went to components and then applied this map. So if I write it as a composition, this means that my psi f after phi must be equal to big phi after psi e. So in other words, that the map phi, which represents our initial linear map in components, must really recreate its action, but in the components with respect to those two bases. And you may notice that all the maps here are linear maps, and more of those are linear isomorphisms. So if I compose this linear isomorphism, then this linear map and this linear isomorphism again, the result, the composition, is again a linear map. That's why we should expect that this map phi from Rn to Rm should be a linear map on the component space. So now let's explicitly write down what this map would look like. So consider, let V be an element of V. And let phi of V, the result of the action of phi on V, be some vector W, well, obviously in W. Then I can write this element W in components. And also I can write the element V in components. So let me do it. Then W equals phi of V equals phi of the sum from I equals to 1 to n of the components of V. So Vi times Ei. Now, importantly, this map is linear. So the sum, the map applied to the sum is the sum applied to the map applied to the summands. So we can take the sum out of the linear map, and also multiplications by the scalar can be taken out of the linear map. So we get that it is equal to the sum of I equals to 1 to n of Vi of phi applied to Ei. This is good. And now notice that this thing here is a phi applied to an element of V, because all basis vectors, after all vectors are in this space, then this whole thing is an element of W. So we can actually decompose it in the basis F. Let's do it here. So phi of Ei is actually what? So it can be decomposed in a basis F. So it should be a sum of J, this is another index, from 1 to now M. Here we'll have some coefficient, and it will be Fj. So this coefficient, it will basically be this vector phi of Ei, jth component. And this is precisely what I will call from now on phi Ji. So now I can plug this expression into our original sum, and it will be the sum from I equals to 1 to n of phi Ji times Vi. So once again, here we decomposed the vector V, and we did some manipulations, and we arrived at our W is a sum of Vi with coefficients times vectors in W, like this. So phi applied to Ei for each I is a vector in W. So for each I, this thing is some vector in W. And any vector in W can be decomposed in the F basis. So it must look something like F basis times coefficients. And this entire thing is a vector, and I write this entire thing in parentheses as a vector, and take its jth component. So we know by definition of the basis that, and by definition of the coordinatization map, that there exist such components which give us the decomposition into the F basis. So, and I call those components you see for each I, it would be j, for each I, it would be m components. And for each I from 1 to n, it will be components phi ji, where I goes from 1 to m, and j from 1 to n, and j goes from 1 to m. So there's n times m numbers. Nothing more, nothing less. Just n times m numbers. And using those n times m numbers, we can recreate the expression like this. So, and of course, I forgot. Yeah, I forgot some basis vectors, precisely. Because of course, okay, we plug in the entire expression in our sum here. So this is actually, we have another sum. So this would be vi times the sum of I of now j equals to 1 going to m of phi ji, and of course fj. Yes. So now this is what we wanted. The sum of these times the sum. Okay. Yes, this can be rewritten because those two sums are over different indices, and this can be rewritten as the sum over j first from 1 to m of, and here a little expression of the sum of I equals 1 to n of the I times fji, and since fj does not depend on the I, it can be written here fj. So we just rewrote the expression here and put this sum forward and this one here inwards. So now what we see is that w is actually has an expression in this basis f, in the basis of w, using those coefficients. And those are actually just wj, fj, for j going from 1 to m. So we can now write the expression w equals phi of v in components as wj equals sum of phi ji times vi, where I goes from 1 to n. And this is our main result here. So we took the expression w equals 5v and translated it into coordinates, and now it looks like this. So once we have chosen two bases, a basis in the vector space v, a basis in the vector space w, we know the coordinates of v, we know the coordinates, we know how to construct the coordinates of v, how to construct the coordinates of w, and we can recreate the action of a linear map using such n times m numbers. So the definition is that given all written, that phi ji are called the components of a linear map phi. Of course, with respect to the basis E of V and with respect to the basis F of W. So those are the components. So now we are very powerful because we can represent components of vectors with n numbers, and we can represent components of linear maps with n times m numbers. And that actually empowers us to do some witchcraft, because instead of writing expressions like this, we can now introduce the matrices and the column vectors. But this can only be done after we have defined everything in a rigorous way and once we understand what it is. So let me clean the board. So our result was that given the expression W equals phi of V, and given two bases on those two vector spaces, where phi is a linear map, we could recreate this, writing phi j, oh, this is I, writing phi j equals phi j I vi. And also a little comment. Yes, I do write the components of the linear map with one index up and left and one index down and right. And this is again just a convention, which turns out to be very convenient because, for example, here I forgot to write a sum, but what I actually mean is that a sum of over I equals to 1 to n, but it is again a very common convention to just drop this summation sign, because you have one index up, one index down, and you sum over them to get the result. This is the expression we had in components. Now the question, or the idea, what if we stuck our components of vectors into columns and components of linear maps into tables of numbers? So what if we stack the components of vectors into columns and the components of linear maps into tables? In the following way. So we can then write this expression as follows. We write W1 to Wm, okay, equals to phi 1, 1, phi 1, 2, now phi m1, phi m2. So you see the column has m elements as it is the dimension of W. So here the upper index was j, and it goes from 1 to m, and the lower index goes from 1 to n. So this is 1 n, and this is phi m n. So as such, we stack the components of phi in a table, which is called a matrix. Now we finally stack the components of V also, V1, V2, Vn into a column. And moreover, we come up with some witchcraft rule, so that we can multiply 511 times V1 plus 512 times V2 and so on, and make a multiply elements of the row times elements of the column, and that would be the first element of the resulting column. Then we do it row by row, and row times column, and we get this vector. And this is what is called witchcraft. Because this is just some mysterious rule that we just came up with, which helps us to replicate this expression in components. And there is nothing objective about stacking vectors in columns and not in rows, or not maybe in strings or anything else, and about this enumeration of elements of the matrix. This is just how we agreed to do it. We also agreed on the matrix multiplication rule. So matrix multiplication would be row times column. And with that, we can do our linear algebra really with matrices and vectors as columns. But you see, and you must see, what stands behind this expression, that there's components of vectors in a certain basis, E here. There's components of the vector W also in a certain basis, which is another basis of another space F here. And those are the components of the linear map phi in respect to those two bases, E and F. And this is how the matrix multiplication works. So now you see that this matrix can be seen as a linear map from Rn to Rm, because of course if you take the sum of two such columns, if you multiply it by a matrix, you get a sum. If you multiply by a scalar, it gets out, you also get the multiplication by this scalar. So this matrix can actually be called this big phi in question, which we drew in the commutation diagram. That if we first go to the from the components of Rn into the vector space V, then we apply our map phi, and then we go back to the coordinates, but now in the basis F, this would be our phi. Good. And what we are left to do is one final little chapter is about the change of basis. So chapter 4, change of basis. But for a minute, let's come back here. And it will be a good exercise to show the following. What if one has a composition of two maps, say phi and, for example, chi? So we have a composition of two maps, two linear maps. And here we have a matrix phi corresponding to this. Here we have a matrix big chi corresponding to this map. And those are two maps, of course, from some vector space U and chi to V, then phi to W. We know that the composition of two linear maps is again a linear map, And if you choose 3 bases, one here, here, and here, we can represent the components of this linear map. So the exercise for you is to show that the components of the composition of phi after chi can be represented with a matrix, which is just the matrix multiplication of phi times chi, where we use this witchcraft matrix multiplication rule, row times column. So this exercise. So now the change of basis. And now let V, again, maybe plus dot be an n-dimensional vector space. And also let E from 1 to En and E twiddle from 1 to E twiddle n be 2 bases of this vector space. Of V. Then what is a change of basis? So we can express, so the vectors which form the new basis also vectors of V, which means that they can also be expressed in terms of the old basis. So suppose this is the old basis, this is the new one, and we want to study how the change of basis works. So I have a vector space with 2 bases, and we want to study how to change from one basis to another and how the components of, for example, a single vector would change. But first of all, let us define how those 2 bases are related. As each element here, the new basis, it twiddle, is also a vector in the vector space V, it can be decomposed in terms of the old basis. So let us take the general element Ej twiddle, and it is equal to the sum of some coefficients in the old basis Ei. What are those coefficients? Those are precisely Ej ith component for I from going from 1 to n. And you see those for each j ranging from 1 to m, we define n component, ranging from 1 to m, thank you. This would be, again, n components. So this expression here for each I and j in total would form n times n numbers, so n squared numbers. And we can call those n squared numbers, we can just call them A, ij. So just by definition, this would be A, I, j, and in particular, this is n squared numbers. We can also recreate this expression. So this is a vector on the left, and this is again a vector on the right, but nevertheless, we can stack those vectors, and now let me stack them into rows. Why? One explanation, probably not the best one, would be that, well, I have here the index down, and that's why I want to stack them into rows. But another is just because it works. The true explanation is that this is just some witchcraft, and those are just our own rules we come up with how to stack different objects so that our matrix multiplication rules work. But this is how we do it. So what we can do is to write E1 twiddle to En twiddle. If we stack the elements of our basis vector, of our new twiddle basis in a row, and this is just a notation, so each element here is still an entire element of a vector space. But hang on for a second. This can be actually written to recreate this expression as follows. So this would be E1 to En multiplied by the following matrix: A11 times A N1 A1N ANN. This is another reason why for such components I write one index on the left and one index a little bit to the right, because you remember with the expression of the components, we sum over the ith index. So we sum over the lower index here and here, but it's not only lower, it's written a little bit to the right. And that's why when we write V and the components of V, we write this column on the right and we sum over this index I. Whereas in this expression with Ij, we also sum over the index I, but here it's lower, here it's upper, but also it's written on the left. And that's why we want to write also thus this E stacked into a row from the left of the matrix. And we can also multiply a row on the matrix like that. So it will still be a matrix multiplication, row times column, and this matrix multiplication rule would replicate this expression here, where A is this matrix. So good. This matrix A helps us to link those two bases together, going from the old one to the new one like that. Now the final question is, what happens to the components of vectors? So let me take an arbitrary vector V in this vector space. And I can, of course, express it in both of the bases. So V expressed in the new basis is from j equals to 1 to n of V j, I will call those components tilde, the tilde components with respect to the tilde basis, times ej tilde. And now we know how to go from how to express the tilde basis in terms of the old basis. This would be from the same sum from j equals to 1 to n, v tilde j, and now comes the sum I equals to 1 to, again, n, a I j ei. Now we do this similar trick. We just rearrange the sums in this expression, and the sum with I comes forward. And what we are left with is the sum of a ij times v tilde j times ei. And this is exactly the decomposition of our vector v, but in the old untwiddled basis. So this is exactly VI EI. So this expression here is how our components would look like. But now let us write this down. So VI equals to the sum I equals to 1 to n. Sorry, this would be a sum over j equals to 1 to n. And here we also have j. A I j v without j. So what one should notice here is that this matrix A, it maps the basis, it maps the old basis into the new basis. And this expression can also be written in terms of the matrix like that. Let me write it here. So it would be V1 to Vn equals A11 An1 A1n to Ann times matrix multiplication V twiddle 1 to V twiddle n. Now you see the difference. Here this matrix A maps the old basis to the new one. And the same matrix A maps the components of the old basis, the components of the new basis to the components of the old one. What I also didn't say is that when I link the two bases here, this linear map, which maps one basis to the other, must be invertible. Which means that this matrix A must be invertible. Because if I can go from one basis to another, then necessarily I can go from another basis to the first one. So this expression can actually be written as components of V tilde equals A inverse times the components of V. So this matrix, which is the change of basis matrix, it maps the basis in one direction from the old one to the new one, and components in the other direction, from the new one to the old one. And also the summation is done with respect to different indices, because in this expression, we sum over the upper index with the lower index of j, and in this expression, we sum with the lower index of the matrix, upper index of the vector. And that's why we write here E as a row in the front, then the matrix, and here we write first the matrix and then V as a column. So those two rather witchcraft matrix multiplication rules recreate these expressions for the change of basis. So whenever you have a vector space and you go from one basis to another, you'll get actually a linear map, because this can be written as follows. If you have a vector space V, you have a coordinatization E, and you have another coordinatization with respect to E twiddle, it will get you to Rn and also to Rn. Then the change of basis, so here leave the components, say V I, and here leave the components V twiddle j. So this map, or better I write in the other direction, because from twiddle to untwiddle, from the new components to the old components, would be such that this diagram computes. So actually this matrix A can be written as going first from the components in the old basis to V, and then applying the components. So basically, the change of basis map is new vector is the E after psi E Twiddle inverse, which is very logical, because if you think this is a map from Rn to Rn. This is A, which goes as follows. We first go from the Twiddle basis to V, and then change to the basis non-Twiddle E. So this concludes our small, rather brief journey into linear algebra, and these were really the fundamental aspects of it to really understand what is a vector space, what are the components of vectors, and what is the basis, what are the linear maps between vector spaces, and what are the components of those linear maps. So what we learned today is that there are abstract vector spaces, and there is a rigorous abstract definition of a vector space that it is a set equipped with two operations of addition and scalar multiplication, that the structure preserving maps between two vector spaces are the maps that preserve those operations, and those are called linear maps. And once one have chosen a basis in the vector space, we can go to Rn and write everything in components of Rn. If you have a linear map between two different vector spaces, you choose different bases in those vector spaces, and you write down again the components in there, and you can write down the components of a matrix, the components of a linear map is a matrix, and work in components like that. And finally, if one decides to change the basis, then the change of basis rule changes the components of vectors as follows. Also, a good exercise would be to check how the components of a linear map change when we change a basis. So this also would be some expression with a change of basis matrix, and probably even two such matrices, because we can change a basis in both of the spaces, and with the matrix denoting the components of your linear map. And this is an interesting exercise to do. So this is the end of the lecture, and thank you very much to you all for being here, and I wish you a great day.